This conference will now be recorded.
Hello everyone. So last day we ended at physical properties of water. Some more informations related to water are left, that is structure of water and chemical properties of water. And after that we will discuss hard water and soft water and temporary hardness, then permanent hardness and how to remove those hardness and related problems. Structure of water. So in water there are basically two elements. One is hydrogen, another one is oxygen. So there are two hydrogens and one oxygen. So here you can see the structure. It has band structure and then there is two lone pairs present over oxygen. Now this lone pair and the electrons that are present in this bond, there may be lone pair bond pair repulsion, and because of this repulsion, which is more than bond pair repulsion. So I'm using here different colors so that you can differentiate between these two repulsion. So this repulsion between bond pair electrons. So these two are bond pair. So bond pair repulsion and lone pair repulsion, if we compare, obviously lone pair bond pair repulsion is more compared to bond pair electron repulsion. And that is the reason that the angle, it is leading to a bond angle of 104.5 degree when it is in gas phase. So normally if we consider the central atom oxygen, it is basically tetrahedral, and the ideal angle for tetrahedral, it should be 109 degree 28 minute. But here you can see the angle is basically 104.5 degree, which is lesser than 109. So what is the reason behind it? The reason behind it is this lone pair bond pair repulsion that is more compared to bond pair repulsion. And as a result, to avoid that repulsion, these two, that is the angle between HO and OH bond, that is decreasing. Fine. If we consider polarity between hydrogen and oxygen, as oxygen is more electronegative than hydrogen, so that is why there is del positive charge and del negative charge. When we use del sign we use when we want to express partial charges. Okay, it is not fully developed charge because bond is not broken. We are just trying to see what is the polarity. So this bond, if you consider, obviously electrons will be closer towards oxygen because it is more electronegative, so partial negative charge will be developed, and here it is 2 del negative and del plus over each hydrogen atom. So there is partial negative charge and positive charge on the oxygen and hydrogen atom respectively because oxygen is more electronegative. Now you can see this diagram where you will be able to understand how many electrons are coming from hydrogen, how many electrons are coming from oxygen. So the electrons of oxygen, that is here denoted by this yellow color. So oxygen, if we consider outermost electronic configuration, it is 2s2 2p4. So you can see this is basically 2p, this is 2s. So in 2s we have 2 electrons and in 2p we have total 4 electrons. And here out of these that is 6 valence electron, only 2 are used for bond formation. So this is the bond between oxygen and hydrogen, and rest of the electrons, that is out of 6, 2 used up in bond formation, and rest of the 4 electrons of oxygen that will be engaged in lone pair. So that is why there is 2 lone pair present, as you can see here. Fine. Now the important thing in the structure of water, if we do not talk about it, it will be completely, that is the discussion will be totally meaningless, and that topic is hydrogen bonding. So when it is in liquid phase, water molecules, they are associated with each other by hydrogen bonding. So there is hydrogen bonding between individual water molecules. So as you can see in this picture, these are water molecules where oxygen is in red color and these two are hydrogen. So this is one water molecule, another. So you can see del plus charge is mentioned over hydrogen and del negative mentioned over oxygen, and there is interaction between hydrogen of one water molecule and the oxygen of another water molecule. So here this type of hydrogen bond, total 4 interactions are shown here in this picture. But remember, it is possible only in liquid phase, not in gas phase, because in gas phase they are far from each other. So this is in liquid phase, and also in solid phase there is hydrogen bonding. Though the hydrogen bonding of water in liquid phase, that is liquid water, and solid phase, that is ice, there is little difference. So that we will see in the next slide. So here you can see liquid water hydrogen bonding, and this is the solid phase hydrogen bonding. So if you look at this picture, the first thing that will catch your eye is there is more distance, that is cavity type of thing is present in ice structure, which is not present in water molecules. Okay, and here hydrogen bonds are not so stable. Here it is stable hydrogen bond. Ice has highly ordered 3-dimensional hydrogen bonded structure. Now remember, this type of, that is crystal formation, there is 2 different forms that is possible. If it is atmospheric pressure, then the crystal of ice, it is in hexagonal form. But if it is at very low temperature, then it condenses to cubic form. So depending on the condition, it may have different types of crystal shape. Next, if we consider X-ray crystal structure, from which it is observed that oxygen is surrounded by 4 other oxygen atoms, and they are present at a distance of 276 picometer. So here if you focus on one oxygen atom, if you look at the surroundings of this environment of this oxygen atom, you will see there are total 4 oxygen atoms present, as if they are tetrahedrally present, and the distance is 276 picometer. In ice, hydrogen bonding leads to open type of structure, and there is presence of voids. So see, these type of voids are present here. Now this type of void is not present in case of the hydrogen bonding when it is present in liquid phase. So because of these voids, it can hold some other type of molecules if it matches with the size of the voids interstitially. Now because of this void, this is the actual reason why ice is having lesser density compared to water. And this is the reason also why ice cubes float on water. We know ice cubes float on water, but what is the reason behind it? It must have lesser density because more void is present, volume is present. Fine. Now this also has some biological importance. Because of this characteristic feature, in winter season, the ice that is formed on the surface of lakes, that is in cold region, it acts as a thermal insulation. Thermal insulation, how it is providing the insulation? Basically in these voids, the air that is packed, that air will be acting as the insulator, and it ensures the survival of this aquatic life. Now in the surface, if there is ice, and if the air that is present in the interstitial voids, that air will act as insulator, and as a result the temperature of this inside water that is present inside the lake, outside there is ice, inside there is water, so that water, it will be able to maintain its temperature because of this insulation. And as it is able to maintain temperature, it is now good for the survival of the aquatic life. Because if the whole lake is converted to ice, they will not be able to survive, as the water present inside the lake, it is still maintaining its temperature. That is, a particular temperature is required for the survival, and also the temperature should be such that it is not converted to ice. And how it is possible? It is because of this crystal nature of ice, where air can be present, and this air is actually acting as insulator. Fine. So this is the reason. Next, after structure of water, chemical properties of water. Water, it is very versatile. It can react with different types of substances. It can react with metals. It can react with non-metals. That is, elements we are talking about. Metallic nature elements, non-metallic nature elements, and it can react with compounds also. First, we will see how it reacts with metals. Now, when we are talking about metals, first we will see what about the alkali metals, that is the most electropositive metals. Now, as they are very reactive, they will be decomposed in water even if it is cold condition. So that is why sodium, lithium, potassium, if you touch it with water, there will be explosion type of reaction. Okay, it is very vigorous. And as you are moving down the group from lithium to sodium to potassium, this vigorous nature, it is even increased because the electropositive nature of the metal is increased. So even if the water is cold, there will be this type of reaction with evolution of hydrogen and NaOH, depending on what metal you have taken. So ultimately it is producing some alkaline solution, that is sodium hydroxide in this case. What about group 2 metals? For group 2 metals, except the first element, which is beryllium, we know that the first element of each group, it behaves differently. So in this case also, beryllium, it is not so reactive. So except this metal, the other metals of this group, they also react in a similar way, but obviously less violent reaction. Why? Because when you compare group 1, group 2 metals, obviously the group 2 metals, their reactivity is less compared to group 1. So that is why they are reacting less violently with what? And the hydroxides that are produced, just you have seen in the previous case, we have obtained sodium hydroxide, and here we are getting barium hydroxide. So these hydroxides are less soluble compared to the hydroxides that you are getting from group 1. Now what about transition metals? Transition metals also react with water. Now you have to provide temperature, that is, it has to be hot water or steam. Steam means now it is in gaseous form. Now compared to group 1 and group 2, obviously from transition metals you cannot expect so much reactivity, so you have to provide temperature or steam to form the corresponding oxides. Now we are getting what type of product? We are getting oxides and obviously hydrogen. So suppose you have taken iron and steam is passed over red hot iron. Red hot iron means it is very high temperature, right? Around 600, when we say red hot or white hot, it actually means very high temperature. White hot is basically greater than 1000, and red hot is also high but not greater than 1000. So red hot iron results in the formation of iron oxide, Fe3O4, and obviously with release of hydrogen. So this is the example from transition metal, iron. Then another transition metal, lead and copper also, they decompose water only at white heat. So see, here it is for iron, it is comparatively reactive. So for when it is red hot, that is temperature obviously high, but not the temperature like white heat, because white heat is more temperature. So for lead and copper, you have to provide, that is, if you want reaction, you have to provide this high temperature. And then silver, gold, mercury, platinum, they do not have any effect on water because these are not metals which are very reactive. And see, silver, gold, they are not at all reactive. So that's why we can have jewelry made of silver and gold, right? So silver, gold, mercury, platinum, they will not react with water. In presence of water, there is no reaction. So this is all about the reactions with metals. Next, we'll see how it reacts with non-metals. In the elemental form, the non-metals such as carbon, sulfur, phosphorus, there is no reaction with water in elemental form. But carbon can react with steam when it is red or white hot. That means now it is very high temperature and it will produce water gas. That means mixture of CO gas, carbon monoxide and hydrogen. What about halogens? We are talking about non-metals. Obviously, halogens we have to mention. Halogens react with water and it gives us acidic solution. So suppose you have taken chlorine, and when chlorine is reacting with water, there is formation of two different products. One is hydrochloric acid, that is HCl, very common. Another one is we obtained here HOCl. Now this is known as hypochlorous acid. If we write in general, suppose I am writing X2 plus H2O, then it will produce HX and HOX. HOX is similar to HOCl and HX is HCl. So this is hydrochloric acid, but if we consider HX, it will be hydrohalic acid. And if we consider the general form of HOX, it will be hydrohalous acid. But as we have taken chlorine, the name we are using hydrochloric acid, HCl, and hypochlorous acid, HOCl. Now this HOCl, that is actually responsible for the bleaching action of chlorine water. We know chlorine water has bleaching action, but what is the actual component responsible for it? It is hypochlorous acid. So it is responsible for antibacterial action of chlorine water and can be used as bleach. Fluorine, it reacts differently to liberate oxygen from water. So fluorine, it is the first member, so sometimes there will be some that is its behavior, it may not match with the rest of the members of the group, and it is true for any group 1, 2, and that is from S block and from P block also. The first member, it behaves differently. So as it is the first member, so see here we are getting hydrofluoric acid and oxygen gas. So second, we have seen reaction with non-metals. The third chemical properties of water is amphoteric behavior. So amphoteric behavior means it will behave as acid and also it will behave as base. And that depends on what is the other compound you have taken to react with water. So depending on the nature of this other compound, it can behave as acid or it can behave as base. So it can act as proton donor, that means now it is acting as acid. It can act as proton acceptor, so it is acting as base. Fine. This is acid, this is base. So when you are treating water with HCl, now with respect to HCl, obviously water is less acidic. So now it will behave as base and it will accept proton from HCl. But if you are treating it with ammonia, ammonia is more basic compared to water. So that is why now in presence of water, it will donate proton. So it will behave as acid. So see, when it is in presence of HCl, it is producing hydronium ion because one H that is coming towards H2O and it is forming this type of hydronium ion, and chloride ion is there. And when it is in presence of ammonia, it is it is providing one proton, and as a result now ammonia, after accepting proton, it is converted to ammonium ion, and rest of the part of H2 it will produce hydroxide ion HO-. The fourth behavior, chemical properties, autoprotolysis of water. You can also call it self-ionization. So self-ionization means obviously we are not using any other compound, as if one water molecule is reacting with another water molecule. Ionization of water takes place where water molecule deprotonates in order to form hydroxide ion. So from water molecule, if one H plus is removed, it will be producing HO minus. So as if one water molecule, it is giving proton and it is converted to HO minus. And this is also the conjugate base of this. And as it is providing H plus, so as if one water molecule is acting as base, acting as acid. And this H plus which is removed, that is accepted by the second water molecule, and together it is forming H3O plus, which is hydronium ion. You can also say it is the conjugate acid, but conjugate acid of what? It is conjugate acid of the second molecule. So H2O and H3O plus, if you compare these two, so if this water molecule is base, as it is accepting H plus from the other water molecule, suppose it is number 1, this is number 2. So number 2 H2O molecule accepting proton from number 1 H2O. So that is why now it is converted to hydronium ion, which is also the conjugate acid of the second water molecule. So this is known as autoprotolysis of water or self-ionization. The next chemical property, hydrolysis reaction. Hydrolysis reaction means now there will be some ionic compounds, and because of its high dielectric constant, it is very polar in nature. From a dielectric constant, you will be getting the idea of the solvent, how much polarity it has. Higher is the dielectric constant value, higher will be the polarity. So it can dissolve many ionic compounds. And hydrolysis reaction means basically when we are saying that hydrolysis of any compound, basically we are trying to say that the compound is reactive with water. So reaction with of any compound with water, that is actually hydrolysis. So for ionic compounds, it can dissolve. But what about covalent compounds? So there is certain covalent compounds and ionic compounds. They are hydrolyzed in water also. So certain covalent and some ionic compounds are hydrolyzed in water. So here we have covalent compound SiCl4. When it is reacting with water, it is producing SiO2 and 4HCl. So the first point it is mentioned, it is simply being soluble in water. There is actually no reaction. The ionic compound that you have taken, suppose you have taken sodium chloride, very good example of NaCl. So when you are dissolving in water, there is actually no hydrolysis reaction. It is simply dissolved in water, that's it. But in some cases, suppose you have some certain covalent compounds or even some ionic compounds also, there may be hydrolysis reaction. Fine. So hydrolysis reaction means now it is not that it is simply dissolved in the solvent. There is actually some chemical reactions occurring and you are getting some new products. So from this example, you can see we have taken chloride of silicon, which is in presence of water. There is hydrolysis and we are getting silicon dioxide and hydrochloric acid. In case of phosphorus oxide, P4O10, it is converted to this phosphoric acid H3PO4. Hydrolysis, so these two are basically covalent compound. Example. Now some ionic nitride. Nitride means which is containing nitrogen 3 negative charge ion. So this ion is known as nitride. Do not be confused with N3 minus. N3 minus is basically 3 nitrogen atoms having 1 negative charge, that is known as azide. That is different. This is 1 nitrogen atom containing 3 negative charge, and this anion is known as nitride ion. So when I am saying ionic nitride, basically the other, that is the cationic part, that is basically some electropositive metals. So see here we have Ba3N2, barium nitride, calcium nitride, lithium nitride. So for lithium, which is from group 1, the oxidation state is simply +1. Now to balance 3 negative charge, you need 3 lithium. So that is why for group 1 metals, the formula will be M3N. But if it is group 2 metal, suppose I am writing it with M prime. Group 2 metals oxidation state is 2+. Now here the negative charge is 3 negative. Now the common factor that we have to multiply 2 and 3. So you have to multiply 2 with each other. That is 2 with 3 and 3 with 2. So now it will be 6. So the formula will be M3. Now total positive charge is 6 plus and N2. So total negative charge is -3 into 2 -6. So that is why the formulas are different. It is for group 2 and this formula is for group 1. So Ba3N2, Ca3N2, Li3N, etc. it will undergo reaction in water. So here only the anion is mentioned. If the metal also you have written, it is a general way you can express like this. If the metals are also present, there will be basically hydroxide. So if you have taken Li3N, it will be LiOH. If you have taken barium or calcium nitride, it will be barium hydroxide or calcium hydroxide. But the other product is ammonia. So it will yield ammonia and the metal hydroxide. Okay. So this example that is for the ionic compounds, and this example that is for the covalent compounds. Fine. And there are some ionic compounds where there is no reaction, it is simply dissolving in water. But in some cases there may be actual reaction, and then we are using the term hydrolysis reaction. The next chemical property is hydrate formation. It is actually directly we can't say that there is actually some chemical reactions occurring, but still we discuss it under chemical properties of water. So what is actually hydrate? A hydrate is any compound that has absorbed some water molecules from its environment. Suppose the compound you have taken in water medium. Now what will happen? It will absorb some water molecules and it will include them in its structure. This majority of hydrates you will find they are actually inorganic hydrates, and they are most common, that is major, and they are the ones that are most often used and studied because their numbers are high. So in inorganic hydrates, the water molecules they are loosely bonded to the compound and there is actually no direct chemical reaction involved. Fine. Now how you can remove these water molecules? You can remove these water molecules simply by heating. So when you are heating the inorganic hydrates, there is removal of water molecules. Now how many water molecules will be removed? That may be dependent on the temperature and it may vary to compound. Now once all the water molecules are removed, you can call the inorganic compound anhydrous. But when it is with the water molecules, it is basically the hydrated form. We will see some examples. So hydrate formation, the water in the hydrated salts, how it will remain? Basically, they can remain simply in the interstitial positions of the crystal of the inorganic compound, or there may be some coordinate bond. So both are possible, and both together also may be present. The formulas, that is how we express the hydrate. So suppose the metal salt is, I am simply writing MX2. Now there will be, you have to give some dot sign, and if there are Y number of molecules, suppose N number of molecules, water molecules, so it will be written like this. Fine. So the formulas are represented using the formula of the anhydrous component. So this is basically the anhydrous component followed by a dot sign. So this is dot. Then you have to write the water preceded by a number of corresponding to the number of moles. So per mole of this salt or any inorganic compound, how many moles of water molecules are present? This number is basically that number. So per mole of anhydrous inorganic compound, how many moles of water there? That we have to mention like this. So see, here we have examples: chromium H2O whole 6, then Cl3. Here we have total 6 water molecules, and they are basically, if you are thinking then why we have expressed this like this, basically you can also actual way to represent it like this: CrCl3 dot 6 water. But this formula is more common, and in most of the places you will see this formula. Why? Because here the 6 water molecules, they are forming coordinate bond. So they are attached to chromium by this type of coordinate bond. Total 6. So what is coordination compound? What is coordinate bond? There is separate chapter for this in class 12. But this is actually the structure. But these water molecules, as it is mentioned in the first statement, that they can remain by forming coordinate bond. So normally it is expressed like this at a hydrate, but as it is also coordination compound example, so those compounds are expressed like this. So OH2, here it is making coordinate bond, so that is why it is inside the third bracket, which is also known as coordination sphere. And there is total 3 positive charge. This 3 positive charge is balanced by this outside 3 chloride minus, that is Cl minus R. So that is present outside the coordination sphere. So if you are expressing it in the hydrate form, it should be CrCl3 dot 6H2. Then we have another example, BaCl2 2H2O. Here per mole of barium chloride, 2 moles of water molecules present. And in this case, the molecules are present in the interstitial positions. So first example, they are in present by formation of coordinate bond. The second example that you are seeing, they are present but in the interstitial positions. So suppose you may get some question which is framed in this way. Some examples of hydrates will be there, and it may be asked that among these in which case water molecule is present in interstitial position, then this should be the answer. Come to the third one, copper sulfate 5H2O. Now this is very famous. In this compound, out of these 5 water molecules, it has some interesting feature. Out of these 5, only 4 water molecules, they are present by formation of coordinate bond. But the 5th water molecule, it is present outside the coordination. And it can form intermolecular hydrogen bond with another molecule also. Now, in the next slide, we will solve a question which is based on this, and there we will see the detailed structure of this copper sulfate 5H2. So the question is the number of water molecule or molecules, because if you look at the options, if you choose option D, it will be molecule, but if you choose 2, 3 or A, B or C, it will be molecules, more than one. The number of water molecule or molecules that are not coordinated to copper ion directly in CuSO4 5H2O molecule, that number we have to find. So the number of water molecules, as we have seen in the previous slide, on only 4 water molecules forming coordinate bond. That means one water molecule is not forming coordinate bond. So see, this is the structure. Here we have copper 2 plus, the 4 water molecules in red color that are forming coordinate bond. Coordinate bond is expressed with this type of arrow sign. And the sulfate ion that is present. So suppose for this copper 2 plus, the corresponding sulfate is here. Now sulfate ion is SO4 2 negative. Now this negative charge over O minus, and there is another type of oxygen which is doubly bonded with sulfur. This oxygen is making hydrogen bond with the 5th water molecule. And this 5th water molecule, there is another copper 2 plus center, another sulfate. So as if this water molecule, these two hydrogens, they are making hydrogen bonds. You can see here another water molecules, hydrogen bond. And this sulfate, which is suppose with this copper, there is another copper 2 plus center, and there will be another sulfate here. That is, this is one copper sulfate, this is another copper sulfate, and they are also linked with each other by this type of coordinate bond. So this is the detailed structure that is not needed. You just have to understand that the water molecules, 4 water molecules directly attached, but these water molecules is completely different. This is the 5th one. There is no direct attachment with copper. So that is why correct answer should be option D. Next we have after water, and that is chemical properties of water. What is hard water and what is soft water? Now hard water, when we are saying, we have to understand how the hardness is generated. Hardness is generated because in water, it is actually not always in pure form. That is, if you take some water from different source, it is not that only water molecules are present. There is also some metal salt impurity. So depending on what type of metal salt impurity is present, it may have hard nature or soft nature. If there is presence of bicarbonate anion, chloride anion, or sulfate anion salt of not just any metal, these two metals, Mg2, that is 2 plus will be the charge, and calcium. So if you have magnesium or calcium salt of all these 3 anions, though sometimes this may be also found, but when we talk about hard and soft water, we are interested only in these 2 metals. So there must be salt of Mg and Ca. Suppose magnesium bicarbonate, magnesium chloride, magnesium sulfate, or it may be calcium bicarbonate, calcium chloride, calcium sulfate. Okay, so if it is present, the water will be called hardness, hard water. Now, how it is contaminated by these salts? It get contaminated when it passes through ground and rocks, because in ground and rocks there may be presence of this salt and they have some solubility. So now they are present in water. Hard water does not produce leather with soap. So this is a characteristic of hard water. And in this way, you can also understand the difference between hard water and soft water. So if you want to make some leather, you will not be able to do so. And instead, what you will get, there will be some scum formation or PPT formation. And why this PPT is appearing? It is because the cations that is present in hard water, that is Ca2 plus or Mg2 plus, they will react, the cations will react with soap molecule to form precipitate of the salt, calcium 2 plus and Mg2 plus salt of fatty acid. Okay, we'll come to that equation, but first we will see one picture where you will be able to understand what is actually leather formation and what is actually scum or precipitate. So you can see in this picture, in soft water there is simply leather formation and rest of the water is clean water. But if it is hard water, there will not be any leather formation and it will look like this, as if it is something is mixed with it, but still it is not precipitated. It will look like this, fine, and it is called scum. Or if you keep it for long, then there may be PPT. Now, when that is, if we want to understand the equation, we have to know what is soap molecule is actually. So soap is basically sodium or potassium salt of higher fatty acid. Now, what is fatty acid? Fatty acid is basically, if I write it, it is basically carboxylic acid. But remember, it is not just any carboxylic acid. This R group, it is very long chain of carbon and hydrogen. So that is why we are saying higher fatty acid. And this has a special name, fatty acid. Some examples are stearic acid, palmitic acid, oleic acid, etc. Now this RCO2H fatty acid molecule, when they are obviously in sodium or potassium salt form, like this RCO2Na or RCO2K. Now when it is reacting, that is, you have mixed water with soap. Now in water there is already presence of Ca2 plus and Mg2 plus. So now this Ca2 plus and Mg2 plus, they can replace this ion Na plus or K plus and it will take the same place. You see, this is the equation. We have taken sodium salt of stearic acid. Stearic acid is basically C17H35COOH. But as it is so sodium salt, so this H is replaced by Na. So this is sodium stearate molecule. It is soluble. It is the soap molecule. Now suppose you have taken some hard water. You are mixing it with hard water, and in that hard water there is presence of Ca2 plus ion. It may be calcium chloride, it may be calcium sulfate, whatever it is, but calcium 2 plus is there. This calcium 2 plus, now it is replacing this Na and it is taking the place. But as there is only mononegative charge, so 2 of this unit must be attached to Ca2 plus. And this sodium is reacting with the anion. If it is chloride, it will be NaCl. If it is sulfate, it will be Na2SO4. So here we have also taken the example of MgSO4. Mg2 plus, it is also reacting in a similar way because that is also carrying the same positive charge 2 plus. And Na2SO4. Now this is soluble in water, but this is forming the scum. So that is why it looks like this, the solution. So this is the equation why we are getting scum or precipitate. Now hard water, it is not suitable for washing purpose because if there is no leather formation, washing is not possible. And it is also harmful for boiler. Boiler means where water is boiled, because if you boil it, hard water in boiler for long time, that is use it frequently, there will be deposition of all these salts in the form of scale, and as a result boiler efficiency will be lost. Water that is free from Ca2 plus and Mg2 plus ion, that is called soft water, and it can produce leather with soap solution ready. Distilled water and rainwater, they are actually the very common example of soft water. There is because they are distilled. So in distill means we have already removed the impurity. Rainwater, it is directly coming from clouds. So how there will be some mineral? It is not possible. So this is a very common example of soft water. Now, when we talk about hardness, there is basically two different types of hardness: temporary and permanent. Now, temporary hardness and permanent hardness, what is the difference? When it is temporary hardness, it is because of this HCO3 minus, and they are basically soluble salt. We have already seen that hardness is occurring because of these three anion when they are making compound with Mg2 plus or Ca2. Now, out of these three anion, this one is basically temporary, but the other two, that is actually causing the permanent hardness. So temporary hardness is primarily because of presence of soluble bicarbonate of these two salts, and permanent hardness is caused due to soluble salts of Mg2 plus and calcium salt 2 plus in the form of these two anions. So this is the difference. This is for temporary and these two for permanent P. Now temporary hardness, permanent hardness, once we know the difference, next we have to see how to remove this hardness, because hardness, it causes so many problems, but we have to remove it. But the removal process of hardness, it is different based on whether the hardness is occurring, it is temporary nature or permanent nature. If it is temporary nature hardness, then there is separate methods. But if it is permanent hardness, it is the processes are it is not so easy like temporary. Then there is different methods. So first we'll see how it can remove the hardness when it is temporary in nature. So very easy process, it is simply boiling. So when we boil the hard water followed by filtration of the insoluble salt. So if we boil it for a long time, see this bicarbonate, we have already seen that only the bicarbonate anions, they are forming causing temporary hardness. So if you boil it simply, there is formation of calcium carbonate. So as if these two are decomposed, and bicarbonate, from bicarbonate now you are getting carbonate, and these two carbonate, they will be precipitated, and also water CO2, they will be simply, its removal is easy. CO2, it is gas, it will be easily removed, and these two will be PPT in the form of PPT, precipitate. So you can easily do filtration and you will get water, soft water, okay, back. Now in this case, the magnesium carbonate which is formed here, it can further hydrolyze because water is already there to give insoluble magnesium hydroxide. Now magnesium hydroxide, it is more insoluble compared to MgCO3. So it is because of the high solubility product of this as compared to MgCO3. Rather than the precipitate of MgCO3, will get PPT of the hydroxide. So this is the equation. Once MgCO3 is formed, it will further react with water, it will produce MgOH2. So the ultimate PPT that you are getting for Mg salt, it is basically MgOH2. So finally in the medium you will have insoluble CaCO3 and MgOH2. You can remove them by filtration. So this is the first method for removal of temporary hardness. The second method is Clark's method. So this is the alternative method. In Clark's method, now we will use calculated amount of lime. What is lime? Lime is CaOH. So now in the previous case, we have not used any outside reagent, but now we are using calcium hydroxide. So this calcium hydroxide is added to hard water, which is containing Mg2 plus and calcium 2 plus. And there will be formation of insoluble carbonates, that is calcium carbonate, and also hydroxide and we can easily filter. So when it is calcium bicarbonate, you are treating it with calcium hydroxide, you are getting calcium carbonate, it will be precipitated. But if it is MgACO3, there is 2 moles of lime we have taken, and there is formation of calcium carbonate, MgOH. So this is the second method for the removal of temporary hardness. Removal of permanent hardness. Now, permanent hardness, it is because of chloride salt and sulfate salt. Unlike the previous case, that is temporary hardness, where you have seen simply there is precipitate of CaCO3 or MgOH2, and we are simply doing filtration and we are getting back the soft water. But in this case, they do not precipitate out as the temperature rises. That is, simply boiling will not help. So you cannot extract them by simple boiling. There should be some different method. The first method for removal of permanent hardness, adding washing soda. What is washing soda? Na2CO3. This washing soda reacts with these metals, that is basically Ca2 plus and Mg2 plus. They are chloride, they are sulfate. In hard water, they will form insoluble carbonate. So see, this is the reaction. In general, here it is written M. M is basically Ca2 plus or Mg2 plus. There is formation of CaCO3, MgCO3, and these two, there is no problem because they are simply soluble. They are not reason for hardness. But these two must be removed if we want to remove hardness. This is the first method, adding washing soda. Second method, Halogens process, or it is basically the process where we add sodium polymetaphosphate. Now, which sodium polymetaphosphate we take? We take sodium hexametaphosphate. Simply this poly term, now it is exchanged by the term hexa, then metaphosphate. Look at the formula, Na6P6O18. It is also known as Graham's salt, and its commercial term is Halogen, so that is why the name is Halogens process. When you are adding it to hard water, then this following reaction is taking place. But see, now this formula, we will write it differently, because this formula is basically simple formula where you will be able to understand to identify how many sodium atoms are there, how many phosphorus, how many oxygen. But actually, it should be represented like this. This is a coordination sphere. Inside there is 4 sodium together with 6 PO3, and now rest of the negative charge, that will be satisfied by 2 sodium ions that are present outside the coordination sphere. Okay, so here total positive charge is 6 plus and total negative charge PO3 minus, it is total 6 negative charge. 6 negative charge, 4 is 4 negative charge already balanced inside the coordination sphere. Rest of the 2 negative charge will be balanced by Na2. So we are using this formula here because why we are using this formula? Because with this formula you will be able to understand this equation in a better way. So this is the cation. It may be Ca or Mg with its chloride or sulfate anion. Then when it is reacting with Graham salt or Halogen, we are getting this. So what is happening here? This inside Na, now it is replaced by 2M, and see, basically 4Na plus, that is equivalent to 2Ca 2 plus, because total positive charge is now 2, so only 2 is enough, or it is also equivalent to 2Mg2. So that is the reason when 4 sodium plus is replaced, there is only 2M. So see, in this formula, it is easier to understand this equation, and 4Na plus removed, and the anion that is present with M2 plus, it may be chloride or sulfate. Now it will form NaCl or Na2SO4. So in this way, the complexes of calcium or Mg that is formed, this one, it will remain dissolved in water. But if you are thinking that still Ca and Mg present, but see, the water will behave as salt because here these two ions, they are not free. They are present inside the coordination sphere. They are not free. This is actually free, which is outside the coordination sphere. But inside metal ions, they are not free to react with soap. So there will be no problem that some scum or PPT will be formed. No, that will not happen. It can form leather, as they have been tied up in the anionic part. So this is the anionic part. This is the cationic part. And in the anionic part, it is trapped. So there is no problem of hardness. This is the second method. The third one, ion exchange method. It has also different names. Why you should know all the names? Because when you will get problem for solving, different names may be mentioned. So suppose in the question it is mentioned zeolite process. So if you only know this name, you will not be able to understand the process. It is also known as permutate process because zeolites are also known as permutate. Okay, so total three names: ion exchange, zeolite process, or permutate process. So this is a treatment that involves exchange of ions. So that is why we are calling it ion exchange. And for this exchange of ions, we are using zeolite. That is why it is also known as zeolite process. So what type of exchanges is occurring here? Here Mg2 plus and Ca2 plus, they will be replaced by Na plus. Now Na plus, it is not the reason for hardness. So the ions present in hard water, it will be replaced by less damaging ions Na plus from the exchanger. So in the exchanger, there will be presence of Na plus, and the hard water that will be passed through this ion exchanger bed, which is called zeolite. Fine. So what is zeolite basically? Zeolites are hydrated sodium aluminosilicate. This is the formula. This is not something very easy. There is actually so many elements are present. See, sodium, aluminium, obviously oxygen, even silicon. And X number of SiO2, this X may vary. So there are actually different types of zeolites, but this is the general way how we can express it. And water molecules are also there. So see here, these Na plus ions that are present, they are having porous structure where monovalent Na plus ions are loosely held. Now these ions can be exchanged with the hardness producing ions, these two. Now this form, that is large structure of zeolite, how we can express it simply? You can express it like this. So Z for zeolite, and suppose there is 2 sodium. Why we have taken 2 sodium only? Because 2 sodium is equivalent to 1 Ca2 plus or 1 Mg2 plus. So that is why we have written it like Na2Z. Z is rest of the complex structure. And now sodium plus is free and Mz. So now in the exchanger, these ions are trapped. Now suppose all the Na plus, they are exhausted. They are removed. And there is only Ca2 plus and Mg2 plus. It is already attached in the surface of zeolites. Now what to do? You can easily regenerate the previous structure of zeolites if you simply treat it with aqueous NaCl. So NaCl is source of Na plus. Now these metals which is already present, that is caught or trapped in zeolite surface, they will be released again and they get replenished with, that is Na plus will be back. So it can be again used. So this is a good method because you can use it several times. It is less costly. Fine. So this is the third method. Fine. There is another type of exchanger. So in this case, we are exchanging Na plus with Ca2 plus or Mg2 plus. But now there is another type of exchanger which is organic ion exchanger. So in this case, the ion exchange resin technique, that is this technique, why it is better than the previous one? Because in the previous case, you are removing only cation, but it can remove both cation as well as anions. that are responsible for hardness. So these are complex organic. So you can have one problem, that which ion exchange there is possibility for removal of both the cation and, then the answer is this one. So in this case, these are basically complex organic molecules having very large structure, giant hydrocarbon framework, carbon hydrogen framework. But we are not interested in the total structure. We just have to understand that in this giant structure there is presence of these two type of groups. Now these groups are acidic groups. So rest of the structure, if I am expressing with R, then it should be written like this. So these type of acidic groups are present, and also these type of basic groups are present. So either it is containing this type of acidic groups or basic groups like HO minus and NH2 minus attached to them. Now the resins that are with acidic group, they are capable of exchanging the H plus ions for the cations. So H plus is equivalent, it will be equivalent to cation. In the previous case, you have seen Na plus exchange with Ca2 plus NH. Just in place of Na plus, now you will have H plus, which will come from these two groups, and they are called cation exchange resin. But if you have basic groups like hydroxide ion or amide ion, then it will be called anion exchange resin. So we will see the details of this method in the next class. Today we are ending the session here. Thank you for listening.